Our next look at stoichiometry is to look at titrations. So how does that work in terms of using oxidizing agents and reducing agents instead of acids and bases? So what happens usually is that either the titrant or the sample is going to be a strong, and usually you want this to be a spontaneous reaction. So you're going to use a strong oxidizing agent. And the two that we use most often are permanganate and dichromate. And part of the reason is because they have a particular color that changes. So you'll see the permanganate goes from pink to colorless when the reaction occurs. So your endpoint, right? Where you can actually detect that equivalent volumes of moles have been added. So the other one is dichromate. It goes from orange to green. Not used as often because it's very hard to tell the difference where it's going from orange to green. Going from a color to colorless solution is very easy. I do have a couple of pictures of this for you. So what we've got here is I've got in the flask here, you can see the permanganate, very dark purple color, and then it's being added to an acidified iron solution, and you can see that its color disappears, and it actually ends up a pale pink when you reach the end point. So here's an example, another one of a titration, again with permanganate. You can see the very dark color in the burette, and then you can see that the solution is clear, and then you reached your end point where you've got a very pale pink color. So a couple of other things here, and it says it's often necessary to standardize the titrant, and standardization means that you have done an earlier titration to figure out the true concentration of your titrant. So a lot of times when we use KMNO4, what happens is that it's such a strong oxidizing agent that over time, if it's stored, the solution will actually lose a little bit of strength. And so what happens is by doing a standardization with another substance whose concentration you know very accurately, you can actually determine what your concentration is very accurately, and then do your titration. All right, now a couple of things, reviewing of the lab equipment. So your titrant is placed in a burette. So that long skinny tube with a tip that is graduated with mils. Inside the burette, we have the titrant. So that's the liquid that is being added to our sample. Remember I didn't label this, but you use an Erlenmeyer flask to prevent the liquids from spilling out. It's cone shaped, kind of helps keep the liquid inside. And your volume is controlled by what's called the stopcock. So remember that if it's in line with the burette, you've got your titrant flowing into the flask. If it's horizontal to the burette, then it stops, the liquid stops. All right, the other thing with this is that you've got these tables with the data. And remember that you have to kind of deal with the numbers in these table before you can do your stoichiometry question. So remember that you're going to subtract these values. And by the way, and I need to talk about significant digits with these. So because you are subtracting, remember your significant digits are going to be based on decimal places. And it's this column after subtracting that you're going to use for significant digits. So this number here, I've got 2 significant digits, but I'm not going to use it because that's just the placeholder of the tool. I want to use the value that I obtained after subtraction. So this is 11.5, 11.2, 11.1, and 11.1. And in high school, we basically say that as long as numbers are within 0.2 mils of each other, you can keep them. This first value is too much away from them. It's 0.3 away from our nearest number. So we're not going to use it. That's going to be an extra one. And to find our volume, we are going to take the average of the last remaining numbers. So by the way, You can have 4 numbers here, you can have 5, you can even have 2. It's better to have 3. It just kind of makes sure that you're not making a lot of mistakes. So what I do here is 11.2, 11.1, 11.1 divided by 3, and that gives me an average of 11.13 ... mils. Okay, so I've condensed all the information in the table into one number here. All right, so now that I've dealt with the table, let's go and see what problem I'm solving. It says a 0.0114 mole per liter KMnO4 solution is titrated to oxidize 25 mils of chromium 2 ions to chromium 3 ions in an acidic solution. The following results were obtained. What is the concentration of the Cr2 plus? So I know that I've got K plus, MnO4 minus, okay, and I am titrating chromium 2 plus ions into chromium 3 plus ions. I don't have chromium 3 plus yet. That's going to be my product, which kind of again gives away a little bit what's happening with that chromium. And it's in an acidic solution, and because everything is in a solution, I've got water there as well. All right, so oxidizing agents and reducing agents. So I go back to page 7 in my data booklet, and I look up everything that I've got here. So I've got permanganate this time around. So I have, where are you? Potassium permanganate right there. I know, and it's acidified, so I've got hydrogen as well. I've got potassium ions, and I've got water on the oxidizing agent side. And I've got chromium 2 plus as well. There it is. On the reducing agent side, I've got water. And please remember that chromium is one of the ones that can be both an oxidizing and a reducing agent. So for this one, if you take a look at it, it's the first substance as we go up from the bottom. It's going to be my strongest reducing agent. And then my strongest oxidizing agent is the permanganate. And one of the nice things about any sort of stoichiometry or titration kind of question is that the stuff that's in your beaker is the one that's undergoing the redox reaction. So in that sense, it makes the titration questions a little bit easier. So the permanganate plus hydrogen is an oxidizing agent. Hydrogen is an oxidizing agent. Chromate is both. All right, so my strongest oxidizing agent is my permanganate. So MnO4 minus plus 8H plus. And again, remember, as always, I'm getting these values directly from, what am I doing with the chromium there? I'm getting these values directly from my data booklet. Okay, so if you're wondering where I'm getting these from, it's page 7. So there's my strongest oxidizing agent. My strongest reducing agent is going to be my chromium ions. So 3 plus, 2 plus, goes to Cr3 plus 1 electron, which means I need to multiply this by 5. All right, so overall, MnO4 minus plus 8H plus 5 Cr2 plus gives me Mn2 plus 4 water plus 5 Cr3 plus. All right, I'm going to write down the information. So I have a 0.0114 mole per liter potassium permanganate solution. And by the way, for this, how do I know that the potassium permanganate and the permanganate have the same concentration? Well, think about it. KMnO4 dissociates into K plus and MnO4 minus. I forgot to mention that in our last time, the last equations that we did. So that's why I know that that concentration of KMnO4 is the same as MnO4. And by the way, we will never give you anything that's not a 1-to-1 ratio. All right. And I'm titrating to oxidize 25 mils of the chromium 2 ions. I need one other number, and it's this 11.313. Okay, because that is the KMnO4 volume. So now I'm ready to do my stoichiometry. So for this one, I'm going to take my volume, remembering it to change to liters, and multiply that by my concentration. My next step is a mole ratio. I do want to find out the concentration of that chromium ion. So I have 5 moles of chromium 2 plus at the top of my fraction and 1 mole of MnO4 at the bottom of my fraction. So my moles of MnO4 are gone. I now have moles of chromium. And so now what I need to do is divide by the volume, again changing it to liters to end up with my concentration in moles per liter. All right, so you can see then that the steps are still stoichiometry steps, but you've got the extra step of trying to figure out what to determine with the data collected from a lab. So besides doing a few practice questions using titration and stoichiometry, I'm going to have you do a virtual activity where you are doing some calculations as well using a virtual format. So I do have a few videos for you guys to refamiliarize yourself with the process of titration and making a solution. Not that you will have an opportunity to do that. You will a little bit virtually in the virtual activity, but I just thought it'd be a good idea to refresh that knowledge because it is a skill that is expected that you know how to do in chemistry.